Okay, we are back. We are back. Now I just gotta find out where I left things off. Okay, so we're building an AC-DC converter, a quasi-resonance flyback converter, and this is my old project, an FC reader project. I'll also continue doing that. This will maybe be a future episodes, but for now I really want to get back into power electronics. And yes, just to recap a little bit what we're doing, we're building a quasi-resonance flyback converter. Here's just a basic operation of it. So the idea is that we have a universal input coming in, so 90 to 265 volts AC, and this is quite noisy. So we need a input filter for EMI, electromagnetic interference. And this filters noise in both directions. So both coming into the filter and going back out, I guess, is what I meant by that. This is the challenges of having, a break. Then we have a filtered AC linear signal. Then it goes to a rectification stage where we strip away the negative portion. And we have a pulsed DC signal. Then the active power factor correction, which ensures input current is in phase with input voltage. So what we get is a in-phased pulsed DC, so low frequency, and we have this driver. We selected this Infineon ICE 5Q SPG QR controller IC, which has a driver. It goes to a switch, and then we get an in-phase pulsed DC. Again, only we get higher frequency. That into a transformer that has isolation barrier. And then we have the step down DC. Then again we go through a rectification stage, the output diode, and then another output filter, and then we get a stable DC output, 12 volts. And then we use that back to a reference amplifier to optocoupler. We still maintain that isolation. Back to a PWM driver, or this IC. So roughly what we're doing. I need to recap more of this myself. But where we left off is selecting components. So we have some undecided still. And then we have some selected components. So here is all the stages roughly. Rectifier. We don't have a EMI filter here yet. We'll get to that. Rectifier, input, capacitor, RCD clamp circuit we haven't selected. The transformer we have selected off the shelf based on calculations to roughly get what we need. Output diode and then the output capacitor. And then the flyback controller, which as mentioned we use the ICE E5QSBG and then the MOSFET. So it needs an external MOSFET. In this case, I think there's also one that has also internal MOSFET. But we selected this at least. And then we have some calculations. So sorry about the ants. Yeah, some calculations. This is the transformer. To recap on all of this. MOSFET selection. The in RCD clamp. And we did select one, apparently. Det betyder att du kan få ditt drömboende precis som du vill ha det. Men jag gissar att det du helst vill just nu, det är att fortsätta lyssna på din podd. Sen kan du ju gå in och se alla våra planerade bostäder. Yeah, I need to get Spotify Premium. Okay. We selected this, which is a diode. So basically we need a with clamping voltage, it needs to handle this 900 volt peak, or roughly. We said, or spike, basically. We need the in reflected voltage and then the V spike when the MOSFET is switched off. So when the MOSFET is switched off, we see this very high spike at this point, and in order to not destroy everything, we need a diode to direct this current this way, or this voltage. So the diode needs to handle that. So it's forward biased here. And then we need a capacitor in order to absorb that energy, and a resistor as well. Okay, power to... Okay. And we have a lot of... This could be actually the RC snubbers and RCD clamps for isolated DC-DC converters. So in this case it's DC to DC, but it's still, you have this clamp circuit or RCD clamp right here. So let's see what we did. RC snubber RCD clamp calculation. The role of the RCD clamp is to absorb the energy released by the leakage inductance. Power delivered to the snubber circuit by the underdamped oscillation is equal to this. And that looks similar to what I've written here. Or it's exactly what I've written there. So we need to find out how much power do we see. or how much energy power delivered to the snubber circuit. So the power we see at this point in the circuit my blinds are opening. Okay, right. Why am I not getting? RCD clamp. Better under damped oscillation. During the falling edge. So this the role of the RCD clamp is to absorb energy. Yes, here I peak is the maximum drain current immediately before the MOSFET turns off. Next, we can calculate clamp resistor value based on the allowed voltage across the snubber. ES equals to V clamp and O is equal to V fly. V fly. And if you've been watching before, we're trying to just make progress. So if we feel like it's stopping up, we don't understand what's going on, just do our best and we move on. So we got the diode. Now we're looking into the resistor. Yeah, see if we can. So RCD. L leak. So the leakage. This is specified in the transformer. Should be. Maybe I have it here already. Leak inductance 14.7. Microhenry.
Hej, det är jag.
Wait, is this correct? No leak. So we've also been following this guide. Output rectifier. maybe we can, and snubber. Let's see here. Snubber circuit. Maybe it was this one we were looking into. Determination of R4. So R4 is selected based on the following inequality. R4 is less than 2 times clamp voltage times clamp minus 4 the leak. Okay, we just follow that. Let's not make it any more complicated. I'll put it on another side and I will write it down here. Now wait with this one. So R is less than 2 times the clamp times, I will find a better way to do all of these. The R reflected. But until then, until I get the time, I will just do it like this. L leak times 5 E. Wait, how do I? So the R has to be less than, I guess, 2 times V clamp times V clamp minus the reflective voltage, the clamp voltage, which we have here, 720, over L leak times primary current squared times the switching frequency max, or 2 times 720 times 720 minus reflective voltage, I think this leak. It says here, if the leakage inductance is taken to be 10% of the primary inductance. The leakage inductance here says max 14.7 now. Leakage inductance. How I interpret that is This is the maximum leakage inductance we get. Cool. So we use that. Done deal. We move ahead. 14.7. 14.7 microhenry times primary current. Wait. 2. 2.32. Where did that come from? That's what happens when you're gone for a little bit. You forget everything. Or not everything, but you forget a little bit. You know, since I'm following a guide, this guide, I forget this is I squared. It says there 2.32 squared. Whatever, I have to go back then. Calculating numerical values here. Okay, it's the peak. Primary current peak. So we have 1.23. They had 2.32. Okay, so 123. I would just do like this, so it's clear. What did I say? 23.
Ursäkta att jag avbryter mitt i din
Where?
egen tid med podd och allt. Jag ville bara säga att vi har massor av bostäder som passar alla olika sätt.
Sorry about Spotify. I need to get premium. The switching frequency max. 200 kilohertz. 200. Okay. We get the calculator. Times 620. Okay, let's see. Mm, I don't know. Square 70. Okay, this is what they got. 77, so they selected 75 kilo. And then we get 14.7 times 23 squared times 200. Ah, wait. Yeah. So times 620 divided by 7 times 1.23 amps squared times 200. 158. Forgot to kilo. Right. 14.7 23 squared times 200. So we have it here too. 444. Mm-hmm. Yeah. Let's go with that. Nearest 32. So we got the nearest is 150 or 160. So let's select 160 kilo. There you go. Let's not make it any more complicated. So R4 must be smaller than. Oh, and it needs to be smaller. Alright. So then we set 150 kilo. And therefore, the RF loss is determined. Yeah, so we can do R power R. And the voltage across this will be clamp voltage. Clamp minus the in squared divided by R, which is what did we say? It was 375. And clamping voltage 720, 365. What's it? Whereby 150 kilo from clamp 720. And min max is 375. 375, 720 minus 375 squared divided by 150. Uh, 372 squared. No. 40 minus 3. Divided by 70. Oh. 720. So like this. 720 minus 375 squared divided by 150. Okay. Approximately 0.7935 watt. Set to 2 watt, including a margin. Yeah, let's just set it to 2 then. Hmm. Oops. So let's look at 2 about 150 kilo ohm resistors. Hmm. Dun, 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 dun. Okay. Let's just check this one out. High power thick film chip resistors. No. Yeah.
Fördjupa dig i musiken du älskar. Ta med dig dina spellistor överallt med nedladdningar offline. Eller spela upp din aktuella favoritlåt om och om igen, utan begränsningar. Få all musik utan att höra ljudannonser på Spotify Premium. Tryck på bannern för mer information.
Hmm. So maximum overload voltage. Okay, but that should be fine, right? 720 minus 375 squared. Yeah, or whatever. Not squared, but that's the voltage drop across the diode resistor. 345. Right. Yeah. Okay, fine. Let's just select this one. So I'll do like this. I'll save it. It feels wrong. Feels wrong, maybe. So what do we have? A power rating. 150. Yeah, like I said, we need to revisit that anyways. Forward selection. No. So wait. but times resistance 150. The square root of that 547 by 50. Max working voltage.
Tänk till exempel att låna tonåringens elmoppe hjälper lite. IFs bilförsäkring hjälper mycket.
So it's stopping a little bit up because I'm wondering, like this one, the max working voltage of 250 or max overload voltage. You can also calculate the maximum voltage across a resistor to be equal to the square root of the product between maximum power loss or the power rating times resistance. Which in this case is 2 watts times 150 K, 300K, and square root of that 550. And the voltage will drop across the resistor 720 minus 375, 345. That's higher than the working voltage. Resistor is higher than the working one. Okay, maybe I should select a different one. Or I used to. Oh. Or is it up close. Wait, question mark. Let's just do it like that and move on. Yeah, this is what we're doing, right? We're learning and just doing our best. Okay, so we're at the capacitor. So the capacitor has to be greater than the clamping voltage divided by the ripple voltage times the maximum switching frequency, or the minimum switching frequency times the resistance. That one is easy enough. Let's see. It has to be greater than the clamp divided by the ripple times switch min times the resistance. C is greater than 720 divided by 50 volt times minimum switching frequency. I'm just gonna use the 55. I'm guessing it's that, but I haven't written it down anywhere, it seems. Nope, it does not look that way.
Hej Matilda, när ditt...
Yeah, let's just use the 55. Times R, where R was 150. So 55 times 150. K is power 3. Right. 1.745. Minus 9. So right. So 1,745 picofarads. Okay, that's it has to be greater than that. This is 1.8 then, or okay. So from the voltage applied to C3, the voltage is set to 640. Okay, so let's see the rating.
Bolagets största hits samlade i en spellista. Lyssna på låtar som Kan inte gå. Ikväll igen. Okay, whatever. We just select 500 volts. Something like that. It seems they selected one, yeah, at 500 volts as well. So which time voltage of the capacitor should be set to the peak value of the input AC voltage. All right. Yeah, so we have 375, so it needs to be higher than that. So the C in was also based on that. Oy, oy, oy. Anyways, capacitor. So I just quickly googled it. Multi-layer ceramic capacitor. Okay, no, not that. So the voltage rating has to be, say, 500 or 400 and up. And 1800 picofarads. Yeah, still have a shit ton. And this we don't need. Star electric. Automotive. Check the price, the cheapest one. Non-stop. 46 left. Percent, 5%. Why not this one? Or maybe smaller package. COG. Let's do this one. Yeah, this is the one. So, C selection is this one. It has the capacitance, it has high enough voltage in order to handle the DC voltage here. And enough capacitance to handle the energy from the leak. The leakage in inductance. Okay. So we can basically set this to so and black and so. So we're closing in. We're We still need to select the diode, the output diode, rectification, and then the output capacitor. But yeah, nice. Like I said, we're just learning here. And, you know, putting it into practice. Just stopping up, just continuing and learning as we go. So it's a big part, selecting the components. Okay.
So that's it. I will end it for today and go to bed. Tomorrow is a new day. Yep. Thank you for watching.